Thank you. Okay, I'm sorry for the delay. I made a mistake with the timetable. So I would like to thank organizers for inviting me to give this lecture. And I did not know that it will be 1 hour and a half. Otherwise, I would go for chalk. But with this, anyway, so this will be 3 lectures on different subjects, a little bit different subjects, and you can see like 3 different segments. So, so I will. I can do it much faster than like 1 hour easily. But if you have questions, please ask me, and I will try to answer. Okay, if I can. So what I will tell today is this. Okay, perfect. So I will start by general introduction and explain. All these lectures will be about higher derivatives. So why we need higher derivatives in quantum gravity and how we can deal with higher derivatives. And then I will touch different subjects related to this. So first I will discuss relativity and explain what is the status of higher derivative corrections to corrections or higher derivative terms in gravity if we go to the quantum level, and why we need quantum gravity in general. Then I will explain what is the problem with quantum gravity, why we say that quantum gravity is an unsolved problem, and how in principle it can be solved. This is the lecture of today, and so I will show you different things, including how we can deal with the problem of stability in the presence of higher derivatives in the recent works like last 8 years about possible confinement of ghost states, similar to QED. And the next lectures will be about decoupling in the infrared and how quantum effects of gravity with higher derivatives become quantum effects of gravity without higher derivatives at low energies. And finally, the last lecture will be about this subject of how we can extract information from effective quantum gravity in the infrared. So as references, I would suggest these new textbooks. The textbook we just published a few years ago with my former supervisor in India. The first part is his lectures on quantum gravity, and second is semi-classical quantum gravity, which I wrote. There are exercises, it's textbook, I think it's the first textbook in quantum gravity. There are exercises and things like that. We just finished working on this, it was just published, handbook of quantum gravity. It's not on, it's of quantum gravity. So it is a huge edition, it's like 4,500 pages. And there are about 10 sections, and each section has about 10 reviews written by best experts in the field. So there are, especially related to this, my lectures, there is section perturbative quantum gravity, which I was responsible, and effective quantum gravity, where Cliff Burgess and John Donoghue were responsible. So you can look there. And finally, some people use these lectures you can easily find in ICTP Cipher in São Paulo in 19. Eduardo Canton, who passed away just weeks after then, organized my lectures. There was shock, but it's like more introductory, much more introductory than I will give here. So some people use this to learn the subject and ask me questions. If you have questions after, you can always write me at this point. No, it doesn't work. So let's go. So yeah, today we shall discuss these issues like semi-classical approach, randomization, ghost. Ghost is a funny word, but it concerns higher derivatives. And what is the difference between complex ghosts and unitary and real ghosts, and why we may have unitary S matrix in the theory with complex ghosts? And then I will discuss this very funny subject of ghost-induced instabilities in cosmology, and it will mention some unsolved problems. And then we deal with confinement of ghosts in supernormalizable quantum gravity and some other subjects. So the part which I will deal today is the last part, concerns these papers. Okay, the last is under consideration; it's not yet published in the journal. Okay, so let us start with the Newton gravity, because the starting point should be certainly Newton gravity. So we know that Newton gravity is a very, very successful theory. All the buildings, all the machines, everything we touch and use is constructed using Newton gravity. So Newton gravity is a very successful thing. So it works from laboratory up to galaxy scale. So you can describe rotation course of the galaxies with dark matter, of course, but using Newton theory. During decades, people thought that there is a problem with the so-called pioneer anomaly, but finally, a group in NASA dedicated to this subject after 10 years of hard work. It was 12 years ago. They verified that no need to modify Newton gravity with the precision of 99%. So everything works very well with Newton gravity. So at the level of Newton gravity, we don't need quantum gravity, for sure. Okay? But Newton gravity cannot be the last word in gravity, because we know that electromagnetism has to be relativistic. Otherwise, we have problems with which people were struggling with in late 19th century. So electromagnetism has to be relativistic, and gravity is not relativistic, because gravity is like a Coulomb law, and electromagnetic theory, we know that Coulomb law cannot be isolated from the rest of Maxwell equations. So we have to make something similar with gravity. And this was done by Albert Einstein, and we have these equations. So I put here cosmological constant because the observations in cosmology show that very small cosmological constant is probably present in the universe. So once again, this theory passed all possible tests. You can take the book of Clifford Wheel, Living Relativity, and see that the list, a huge list of tests and observations concerning relativity, and there is no a single point when we need to modify or change relativity to anything else. Adding cosmological constant is a natural extension, because it's like simplest term you can have on the right-hand side or the left-hand side of this equation. It depends on your intention. So by itself, relativity as a physical theory is perfect. But in physics, there is no theory which is perfect. I mean, no working theory which is perfect. No working theory of everything. We have always theory of something. So relativity is not an exception. And if we go, every theory has its limits of applicability. So if you go to relativity to the very, very special limits, so we meet actually a problem, and this problem is called singularities. So spherically symmetric solutions work very well. As an approximation, you can add a precession of perihelium of mercurium and many other observations and meet no problem. But if we think about black holes, then there is a singularity. The same concerns cosmology. We know that the main experiments today in physics are cosmological experiments, and they attract big money, big collaborations, and so on. And there are many of them. And everything fits very well. I don't speak about Hubble tensions and things like that, because these are, from the general perspective, those are small issues. So, from cosmological perspective, of course, it's very important problem. So, but in general, cosmology is very successful area of application of these equations. However, if we go to special situations, then we meet singularities. Let me show how it works. So in Schwarzschild solution, we have this very simple metric, and Rg is the gravitational radius of the particle or planet or our star. So for planets and stars, this is a very small quantity. Like for Earth, it's a question of 2 or 3 centimeters. From the sun, it's like some meters. So it's deep inside the star or planet. So and this is a vacuum solution. So this solution holds only if you are in the vacuum. So if you go inside the star or planet, there is no singularities. Not in the case when R equal to Rg or when R equals to 0. However, there are stars which are capable to produce singularities. In which sense? So imagine you have a star like Sun, and it is very bright. And it is bright because it uses some chemical nuclear process, not chemical nuclear process. So it's like thermonuclear reaction which runs inside the star. And at some point we know that any gas ends. Okay, you need to go to the station and put your gas again to your car or your airplane. The same with star. At some point the fuel ends, and you need, but the star has no gas to take new fuel. So the star starts to shrink because the pressure decreases. There is no more way to keep the temperature. The star shrinks. Then I will not go into details, including because I'm not expert. So at some point they start new type of nuclear reaction and things like that. But by the end of the day, all fuel ends, and the star transforms in something we call neutron star or white dwarf. And this is a very exotic object, like a small piece of nuclear star, neutron star, can weight like a planet or something huge. It's unbelievably dense quantity. But then what happens is that the gravitational Newton force on the surface is always proportional to the mass of the star divided by the square of the radius of the star. But the mass, if the it is all neutron star is homogeneous, okay? So the mass is proportional to the third power of the radius. So as bigger is star, stronger is the force. So there is a limit, so like 2 or 3 solar masses, that if this original star was bigger than this limit, is Chandrasekhar or Volkoff-Oppenheimer limit, then gravity is so strong that it starts to break the nuclear resistance on the surface of the neutron star or white dwarf, and then it starts to shrink, collapse, and this collapse makes out of this star something which may be smaller than the radius of this horizon, and then this solution applies until R becomes equal to Rg. And so you see that at Rg you have a singularity, because here you have to divide to 0. As we used to say in Juiz de Fora, there is a municipal law in Juiz de Fora which forbids dividing to 0. I don't know whether you have this in Santiago. But in principle it's not a good idea to divide to 0, so here you have singularity. However, this singularity is not physical singularity. So you can change coordinates, because these coordinates correspond to the observer, which is very far from the object, and actually he lives in the same situation with the Minkowski metric, because when R goes to infinity, you see that we come back to Minkowski metric. But you can change coordinates, like to Kruskal, Finkelstein coordinates, and then you see that this singularity as R equal to Rg disappears. However, there is another singularity at R equals to 0. And this is a physical singularity with Kretschmann invariants and other things infinite. So, in principle, this theory produces physical singularity at R equal to 0. Actually, even Newton law, I have to go back. It's not easy. Even Newton law, you can see, has 1 over R. So, even Newton law has the same singularity or similar. So, many people explore Newton singularity instead of this singularity, assuming that this is the same thing. It's questionable, but it's like more or less standard practice. So, anyway, we see that relativity produces singularity. And if we go to cosmology, then we also have qualitatively similar situation, because this is the metric. We call it Friedman-Robertson, Lemaitre-Robertson-Walker metric. And if we put cosmological constant to 0, then we have this solution. This is the solution for a radiation-dominated universe. Why radiation-dominated universe? Because we want to go to the early universe, and early universe was dominated by radiation. The reason was that the density, energy density of radiation changed like 1 over A4, and energy density of matter, of dust, changed like 1 over A3. A is the size of the universe. And energy density of cosmological constant does not change at all. So if the universe would be like 10,000 times smaller than now, then radiation becomes relevant. But it is, if it is 10 million times smaller than now, then radiation is completely dominating. And if it's 1 billion times less than now, smaller than now, then there is only radiation. On top of that, the particles which have mass in the very early universe, they also become radiation effectively, because their equation of state is the one of radiation, because mass is negligible. They are so fast that mass does not play a role. So for this, this looks like a universal cosmological formula for radiation-dominated universe and for any other universe. And then the solution is like that. So you see that A is proportional to square root of T, and the dimensional quantity, which is Hubble parameter, which characterizes the expansion of the universe, goes like 1 over T. So when T goes to 0, it's infinite. Then curvatures are infinite. Energy momentum tensor in the right-hand side of the Einstein equation is infinite. Everything is infinite. And we don't think that infinities have right to exist, so something has to be changed. Now, what can be changed? Actually, you have many possibilities. And the simplest one is just to add some extra terms to the gravitational action, such that there are no singularities. I will show you some examples later on. But people also think that, in principle, this singularity, by the way, a few years ago, Penrose got Nobel Prize for this proof of that singularities are unavoidable in any classical solution of relativity for so-called Hawking-Penrose series. And Penrose is still active, and 1 year ago we had a conference with his participation online, and he gave very nice talk and made good, not questions, but he made very good answers to questions of other people. So, yeah. Some people think that the origin of this deviation from relativity could be quantum effects. What it means? It means that we have to take into account quantum effects. These quantum effects will modify relativity, and then we have disappeared singularities. So let us go to a very standard thing, which is a dimensional analysis. So in Gaussian system of units, there are 3 fundamental constants. Velocity of light, speed of light, Planck constant, and Newton constant. And all other quantities are constructed from these 3, dimensions. And then you can solve in a unique way these equations and find the quantities of the dimension of length, time, and mass. And those you can see that this is a very small distance, 10 minus 33 centimeters. Remember, at 10 minus 12 centimeters, you cannot use quantum electrodynamics. You need to take into account electroweak effects and something else. So it is 21 order of magnitude smaller. Then the time interval is 10 minus 43 seconds. You cannot measure it with your watch or something. And finally, the mass is macroscopic mass. It's 10 minus 5 grams, 10 minus 6 grams is a small poiridium. Okay, so I don't know how, a small piece of dust. So you can see it with your eye in principle, if you have good eyes. So, but if you transform this into particle physics units with C and H bar equal to 1, then you have 1019 GeV, which is so-called Planck energy or Planck mass. And this is a lot, because it is 15 orders of magnitude above what we can have on the LHC, on the strongest accelerator, and 11 orders of magnitude larger than the particles, protons, which come in ultra-high energy cosmic rays. So ultra-high energy cosmic rays, one single proton has energy like the full beam of protons in accelerator. But still it is 11 orders of magnitude smaller than the Planck mass. So if you want to have accelerator of this with this energy, you probably need to make accelerator not with 28 kilometers like in Geneva, but the size of the solar system. And we cannot do it. So what it means? It means that at these distances, at these time intervals, and at these energies, you are going to have something relativistic, quantum, and gravitational at the same time. So according to the standard logic from general physics, it means that we have to meet some kind of quantum gravity at this scale. But which kind of quantum gravity? So if you go to this handbook, as I said, there is 4,500 pages, And in the best case scenario, I understand 1% of this, which I wrote by myself. So the rest is very difficult to understand. But I would classify all possible approaches to quantum gravitational and relativistic to three big groups. One is most obvious and fundamental. You quantize gravity in the way you quantize any other matter field. You quantize also matter fields, and then you form a single theory of quantum. Everything is quantum. Gravity is quantum. Matter is quantum. This is most simple and most obvious. You may say, okay, gravity is not going to be quantized. Then you quantize only matter fields on classical gravitational background. This is a little bit different, but you will see that the main problem remains. Regardless, some people last year claimed that its situation is different. I would say they remain in full glory. And then there is another approach, which, as I understood from my discussion with Felipe, are very popular here, is what I call quantize something else. Means that, for example, string theory goes to this category. In string theory, instead of quantizing matter and gravity, you quantize some artificial object, two-dimensional string, which lives in the so-called target space, which might have like 10 or 26 dimensions, depending on your choice for the basic model. And then you make calculate the conditions of consistency in this space and go back to 4 dimensions, and you get your physics. So you don't quantize matter, you forget about success of quantum theory, QE, standard model, and all this, everything becomes irrelevant, and you expect to get everything from string theory. Which of these three approaches is better? Many people think that string theory is the best approach. Some people say that gravity should not be quantized. Some people spend time quantizing gravity. I will tell you that, in fact, these three approaches have something very important in common. Okay, and in all three cases, you need higher derivatives. And even in case of string theory, you have higher derivatives, and the situation is basically the same as in any other part of quantum gravity. So let me start with the most simple approach, which is semi-classical. So semi-classical approach is based on this formula, I would say. So in the path integral formulation, you need to construct the object, which is called generating functional of the green function. Okay, this J is the source for the matter fields phi, which are object of quantization. But your action and this term also depend on metric. Metric enters here as external source or external parameter. If you remember mathematical analysis, there is an integral, the object which is called integral, which depends on parameter. And this metric is the external parameter. So, so our purpose is to calculate this object, or better, we make the so-called Legendre transformation and arrive at effective action. So we can imagine how it works using diagrams. So this is the effective action of mean fields. Okay, phi is people used to the same matter, but it's mean field, and so it's a result of the Legendre transformation with the logarithm of z. And what happens is the diagrammatic level is something like I illustrate with this diagram. So you see, this is phi cube theory, very nice, simple theory. So you have logarithmic divergences, scalar, okay, here. Then you add external metric. How you do it? If you want to use diagrams, then the simplest way is to parameterize metric in the way metric flat metric plus perturbation, and we construct some power series in these perturbations, h minute. So one single diagram becomes a set of infinite sets of diagrams. So like this one has no h minute, it's the same. Then this guy has 2 internal propagators instead, 3 internal propagators instead of 3, because you added 1 extra vertex with a lot of tails of h minute. This here we don't change the number of propagators inside the loop, but you added a lot of tails in the vertex. Then here you have 3, 3. Now, if you are familiar with quantum field theory, basic, I mean, you know that this has logarithmic divergences because you have, can I write here?
Yes, of course.
Yeah. So because you have Yeah. You have integral over d4p pi, and then you have pi squared plus m squared in Euclidean. And then you have k minus p pi squared plus m squared. And when we go to ultraviolet, then k and m are irrelevant, and you have d4 pi over pi 4, and so it's logarithmic. Very good. So then we understand that if there are 3 propagators, then in the denominator you have 6 pairs. So this diagram, and this diagram, and these diagrams are finite. So you only need to calculate these 2 diagrams in this particular case. Okay? Very good. But this is if you want divergences. If you want finite parts, then you have to calculate much more than this. Now another example. This diagram with the same logic has quadratic divergences. So if you add extra tails of H menu, then this guy has quadratic divergences, but this has 2 propagators, so it gains logarithmic divergences only, no quadratic. This has logarithmic, this has quadratic, and this has logarithmic and quadratic. This has only logarithmic, this is finite, and so on. So this is very famous diagram because it produces the so-called R pi squared contour current. So which means makes one of the differences between quantum field theory in carpet and flat space. Now, what's very important is this diagram, this set of diagrams for vacuum. Because here you see there are no external tails of matter here. So this is the contribution to the action of vacuum, exactly to the correction of the Newton theory. So we see that this guy has quartic divergence. This guy has quadratic divergence. And this has only logarithmic divergence. And the extra powers of momenta go to external lines of H menu. So it means that here logarithmic divergence comes with the 4 derivatives of H menu. This guy is finite. This diagram is finite because in the denominator there are 6 propagators, 6 p squares. So it means now on top of that there is a general theorem which can be proved in different ways. You can, for example, look through this book for some references and so on. That all the quantum terms which appear in this theory are covariant. So you cannot have non-covariant quantum terms.
Excuse me? Why are the those are gravitons, right? The squiggly?
Yes, sure.
Why do they appear on multiples of 3?
Multiples of what?
Of 3? Why are there always
Because
3?
when I draw these diagrams using Axodraw program,
Oh,
so I was lazy and did not put more. Okay? But it's very good question. Yeah. In fact, you can have 1, 2, 3, 4 until infinite. Okay? And all this is not important because it's actually a very good question. It's very not important because if you take these diagrams, for example, with one tail here and one tail here is completely sufficient to find divergences. Of course, these other lines become important only if you go for finite part. And only if you go to finite part, which is cubic in curvatures. Okay? So, because covariance is a very strong instrument. As far as you prove covariance, and there are several ways to do it actually. Okay, like in this book, I think I explained very well. So things simplify a lot. So you may think, okay, I have infinitely many diagrams, it's infinitely difficult. No, much on the opposite. You have only just a very few diagrams you really need to calculate, and your general theory covers the rest for you. Okay? So what we find is that these diagrams require 4 derivative contour terms. It means that if you want to have renormalizable theory, you need to put 4 derivatives to the classical action. What means renormalizable theory? As far in quantum field theory, everything you calculate is infinite. Basically, you cannot calculate something which is finite from the very beginning. Very difficult to find. Then you have to extract, remove divergence. This is a simple part, and extract the finite part. And this extraction of the finite part can be done in a controllable way only if you put all possible divergences, the structures of all possible divergences, to the classical action. This procedure is called renormalization. So it was discovered in middle of the 20th century, first in QED and then other theories. So we won't have renormalizable theory just because it's simpler. It's not because we like to have it or not, because in this way our life becomes more controllable. Good. So what it means in reality? It means that if you remember covariance and then you see that your action of vacuum, action of gravity, should include action of Einstein-Hilbert with cosmological term. Without cosmological term, the theory is not renormalizable, so it has to be there. And the value of lambda is defined by renormalization condition. Okay? Then you have R term, of course, and you have this set of 4 derivative terms. One is the Riemann square, second is the square of the Ricci tensor, and square of the scalar curvature. On top of that, there is the box R, which is surface term. Actually, this combination is also a surface term. So why we include these two surface terms to our action? As Professor Banyanis explained to us in the morning, surface terms don't affect the equations of motion. But, well, they do not affect the effective equations of motion at classical level. But the renormalization of these terms may be very interesting, so they are usually included. So it's quite useful to write the action in this way with C squared and R squared, because this means that you separate, because metric has scalar degrees of freedom, vector degrees of freedom, and tensor degrees of freedom. Typically, vector degrees of freedom are gauge dependent, so you can factor them out. But scalars are, R squared is responsible for scalars and only for scalars, and C squared is responsible for tensors and only for tensors. So by the end of the day, if you write in this way, you have two different terms which are responsible for scalars and tensors. R itself has both, has tensors and scalars. Now we can go to, yeah, so you see the main output is that we need higher derivatives. Now if you go to quantum gravity, the situation is like that. You start from any covariant action of gravity. Okay, it can be Einstein-Hilbert action or any other action, even non-local action. And then you can prove the following theory. That this neutral identity, which corresponds to diffeomorphism invariance, holds for the effective action. I can elaborate very much about this, but I will not do it. So it means that your divergences are covariant, and you need to start with a covariant action, classical action, to have a renormalizable theory. Then your form of your action depends on the so-called power counting. Power counting is exactly this story on the next level. So you have to see that if your vertices have P, then this formula changes. Okay, then you still have logarithmic divergences, but it becomes a little bit more complicated. So then there is this power counting formula, which is like a little bit big, and then the so-called topological relation, which leads the number of internal lines, loops, and vertices. If you apply this to your Einstein-Hilbert theory, then you have this formula. This means D is 0, capital D is 0 for logarithmic divergences, because we may forget about quadratic terms, they are not so interesting. So D, small d, is the main hero. It's the number of derivatives of the metric in the counterterms. And P is the number of loops. So in quantum gravity, based on relativity, P is 1, you have 4 derivatives. P is 2, you have 6 derivatives, and so on. At one loop, it was discovered by Hooft and Belkman in '74 by direct calculation, and immediately after that, or almost simultaneously, by Zdezarnim and Poisson. And it was recalculated in like 50 different ways after that. And you have these 3 counterterms. What is curious is that on shell, everything vanishes in the following sense. Gauss-Bonnet combination vanishes on shell because Gauss-Bonnet combination is already 0 because it's surface term. Box are the same. So you have R mu square and R square, and both vanish on shell if you have no matter. So people noted at the beginning that this means quantum gravity at one loop has finite S matrix. Very good. Then it was a big challenge to calculate 2 loop divergences, and Gorov and Sagnotti did this in '86, and they found this counterterm. This counterterm does not vanish on shell. It was later on confirmed by Van der Ven 6 years ago after. So you see that gravity is not doesn't have finite S matrix at the two loop level. Recently, some people, Weber, for example, claimed that this is scheme dependent, but I would say that the result does not change. Okay, because can't be everything independent, right? So I remember, because I'm old man, so I remember time when people thought, okay, gravity is so special, maybe it will be, everything will be fine and enormous. But no, it's not the case. So what is the possible solution? Our quantum gravity is non-renormalized. You can change your standard perturbative approach to something else, like go to canonical quantization, forget about quantum field theory in the usual sense. Go to the so-called asymptotic safety program, okay? Go to string theory and so on. There are many options. You can go or handbook and see that. Or you can just change the theory and take something different from relativity to start with. And so I will only discuss the second idea and just mention string theory example. Yeah, so what we do? First of all, what is the simplest way to have a normalizable theory? It's this one. You just take the same action which you found in the semi-classical gravity. And if you do this, then the power counting is different. You see, the capital D is still 0, but here you have on the right-hand side 4 is the largest possible number of derivatives in the contractor, minus the number of vertices with 2 derivatives, minus 4 times the number of vertices with 0 derivatives. What it means the theory is renormalizable. So in this theory you can calculate everything is under control, everything is fine. But there is one this was proved by Stella in 77 that this theory is renormalized. Right? It's one of the best papers in quantum gravity historically, so I recommend it. But you have to pay the price in quantum gravity. Why? Because if you have 4 derivatives, then your propagator, like in the tensor spin-2 part, has this structure. So you have 1 over k squared minus 1 over k squared plus m squared. What it means? This particle is a graviton. Okay, graviton is a massless particle with a positive kinetic energy. And this particle has negative kinetic energy. You can write it in equivalent form as separate particles, and you will see that this is responsible for the particle with negative kinetic energy. We call it ghost. Imagine you have a ghost. What will happen? Negative kinetic energy means that for a free particle, this particle wants to go to the state of the minimal action, right? So it means that it wants to accelerate. But if it is free particle, it cannot accelerate because there is a conservation of energy. But in gravity, nobody is free because this particle has vertices of interaction with gravitons. So it can simply emit gravitons and accelerate. So it will start to emit gravitons and accelerate. And the mass of this particle is huge, it's a Planck mass. So it can emit a lot of gravitons and accelerate a lot. What it means, remember that the kinetic energy is m mass divided by relativistic root, 1 over beta square. Very soon beta square approach 1. And then the energy of this particle becomes infinite. And when the energy of this particle becomes infinite, we will not like to stay close. And all the universe will not be far enough. So the universe will collapse and we cannot finish our lecture, our lunch, or whatever we do. So it means that actually the existence of such a particle is a disaster. Actually, it's a theoretical disaster because we know that we can finish our lecture and whatever. Okay? So we have to explain this. So from one side, we need 4 derivatives because otherwise you have no stability. No stability because you have no renormalizability. On the other hand, if you have such particle, then you have a very bad situation. These instabilities were first described by this mathematician, Russian mathematician Ostrogradsky in the middle of 19th century. And then at quantum level by Mikhail Veltman in 63, I think it was his first paper. He described it, it's a big paper. He described the scattering of light positive energy particles on a heavy, very heavy negative kinetic energy ghost. And he found that the dominating process is what I said. So the ghost accelerates and the real particles gain energy for free, a lot of energy. So this is not something we can see. If you eliminate ghost from the spectrum, this is a very subtle point. If you remember how we construct X matrix. So you have some in states and out states. S matrix operates between these 2 states. If you construct the initial state without ghost, then owing to the interactions, the ghost is supposed to emerge in the out state. And you have non-unitary S matrix. Is it true? how you can create the ghost from the vacuum? Let's think about it. The constant length of the particle is proportional, is related, let's say, dimensionally to its mass. So for the particle of the Planck mass, the constant length is the Planck length. So you need to concentrate gravitons with the density of Planck mass 4. How we concentrate gravitons in the Planck mass 4? Remember that you have like a problem. How you concentrate photons to create a black hole. Recently there was very good paper by Luis Garay from Madrid and his collaborators about this. They showed that this is impossible because this huge concentration of energy starts to create electrons and positrons, and the energy disappears. So this is just to make a black hole, which is nothing compared to creating this ghost. So you need some very, very high effort to create a ghost. And probably this is the reason we don't have ghosts. The ghost can never be created because nobody can concentrate gravitons with such a huge density. Now, how it works technically? Yeah, we will discuss a little bit later. So, yeah, you can go to more general theories. This is what we did in '97 with Manuel Soreika and Luis Lopez. We introduced this polynomial supernormalizable gravitons. In this case, it's a very nice formula for power counting. All the divergences for n equals 3 or more are at one loop. So at one loop you can have exact beta functions, which is nice. But there is a following theory. If you have a real spectrum of masses, then the signs of A coefficients alternate. So if the first particle is graviton, the next one with the lightest mass will be ghost, then normal particle ghost, and so on. So our intention was to construct a situation when only last particle is ghost and its mass is infinite. But it doesn't work. So the lightest particle is ghost for the real spectrum. At that time, we did not think about complex spectrum. So this is an example of fixed beta functions calculated by us with the first paper and by this gentleman, Leslav Rachkov, and Modesto, and with my participation. For R, there are also formulas for R squared and so on. Okay, but it's all not so interesting. So once again, two sides of higher derivative gravities are the following. You have from one side, you need 4 derivatives because otherwise you have no renormalizable system. And in fact, if you don't put them in the classical actions, they come back in divergences. In divergences come with log of box. And log of box, divergence you can throw out, okay, it's your right. But log of box is something very slowly moving. So it's something which you always observe as a final term, okay? You have the same situation. So how people solve? Actually, there were many attempts to solve the problems of ghosts. I will show you something which is considered standard, okay? Which emerged like 13 years after the first attempt, which we discussed later. This is called Simon's approach. What Simon said? Simon suggested that all these 4 derivative terms, doesn't matter, quantum corrections or classical, should be by definition treated as small perturbations compared to Einstein's theory, like in QED. In QED, he said, there are also 4 derivative terms in the 1 loop corrections, 2 loops corrections, and so on. But they are always has to be treated as small corrections because otherwise you get the so-called runaway solution. And here's the same. And then everything works. You have no second pole. You have only one graviton. Okay, everything is fine. But there are some questions. For example, should we treat R squared as perturbation? Because it's not uniquely defined, let's say. Should we treat R squared as perturbation? Because R squared is treating R squared as perturbation, you have to forbid the Stravinsky model. And Stravinsky model is observationally the best model of inflation. On the other side, R squared does not produce ghosts at all. R squared is innocent. So why you kill innocent, okay, and lose Stravinsky inflation, which is observationally well, let's say, defined theory? Because you want, but why you want that? It's unclear. Moreover, you have many other questions. You make you different from QED. You have to treat these terms as small corrections at home. So there is no technical reason to do this, because in QED we know that they are perturbative weak corrections, and they have to treat it. We have to treat them as perturbative small corrections. Here, no, they may be not small at all, because if you go to high energies, and remember that the main motivation is high energy, then these terms are not small at all, which you say are small corrections. And second, we don't like to define things in the way we like, okay? So in quantum field theory, the general strategy is to calculate things and understand them and not make definitions. So let me discuss a little bit a few ghost-free theories, and I will start with the string theory. This is when you can see things most explicitly. This is the sigma model approach to string theory. So it started in '85 with the papers by Fratkin and I will say it on the next transparency. This column Friedan Martinez Perry. And how it works. So it's two-dimensional theory of the field X, which we interpret after as coordinate in the target space, so our coordinate. So you quantize this field which lives in the two-dimensional space. It's good strategy because in two-dimensional theory everything is renormalizable basically. Things improve in this department. Then you have terms which have 1 over alpha prime. Alpha prime is the parameter of the loop expansion. This is the symmetric, which it will become metric after, and this is anti-symmetric term. Then you have two terms which have no alpha prime. Okay, and this is called dilaton term and what people call tachyon term. So the idea is that these two terms, the first two terms, possess so-called Weil invariance. It means that your theory is free of ghosts. It's basically a very similar situation with ghosts, but I will not go into details. So, but then these terms violate this. You have ghosts with these terms, but they have no 1 over alpha prime, so we have to treat them as one loop corrections, even at the classical level. Then you calculate one loop corrections, and you get terms which contribute to this, and that. And you require that in the next order in alpha prime, you have no ghost again. You require Weil invariance, cancellation of anomaly. Then you get your equations for G, A, B, and T. Then you make new loop, one more loop, one more loop, one more loop. So after this, you get something like effective action of external fields of G. R is the curvature of G, of the metric G. And this is what Fratkin and Setin and Friedan Martinez Perry discovered. The lowest order term is R. These terms produce effective equations, the conditions of cancelling anomaly. So you see, things are very good. If you forget about the second line, you have this R. That if phi is constant, you have exactly Einstein term. You generated Einstein term from the string theory. 1 year before that, I asked my supervisor, why we don't do this string theory? We understand how they do. And he said, no, it is a strange thing with no localities. Nobody will ever care about it. And after months, after this first paper, everybody did only string theory. so it was like an explosion of interest. And the small detail is that if you go to the next order in alpha prime, then you get back your R square term. However, the gentleman called Barton Zweibach, he suggested how to fight this. Let us remember that G is an external metric. So we have to make a reparameterization of external field. It's our right to do it. Certainly, yes. So you make this reparameterization and choose x1, x2 such that this returns 4 Gauss-Bonnet combination. So A2 is minus 4A1 and A3 equal to A1. Then you have no ghosts. Very good. Then next term will give you the same guys with the box in between. You add more terms in reparameterization and you remove everything. This was done by Zweibach, then some next papers were by Desiree, Satan, and other people. So this is the way string theory resolves the problem of ghosts. And in some sense, it's not perfect. Let me explain in which. First of all, we made this observation with Antonio Maruta in '97 that actually this is not a well-defined procedure. Because remember, I made a mistake in R squared. when I make a mistake in x2 coefficient, then you get back your r squared. Should we kill r squared? Not really. Because r squared is good, r squared does not produce ghost. R squared makes Stravinsky inflation and so on. So why we should kill r squared? Well, no answer. I asked three people, and the answer I got was the following: we kill everything we can kill. I like it, but the question is why we do it. But recently we understood with Bruno Guccini, who was at that time my student, not my student. He worked with me, but he was a student of other guy. So that this reparametrization of Zweibach reparametrization must be absolutely precise. This is very subtle point. Imagine I make a mistake of 10 orders of magnitude in x1. What it means? It means that I get back the square of the wild tensor, but the coefficient is 10 in 10th power, positive. So it means that instead of the ghost of the plane mass, 10 minus 19 GeV, you get 10 29 GeV ghost. And it will destroy us even faster, okay, if you follow the standard logic. So this fine-tuning for infinitely many coefficients must be infinitely precise in all these coefficients, except x2, I would say, okay? So what it means? It means that, for example, if you like quantum field theory, you like QED, you have to trust that string theory has to predict QED and all its loop corrections up to 10 orders of magnitude in the electron anomalous moment, magnetic moment of electron muon, with absolute precision. Because if I make this, it means that I changed the world, okay? So literally speaking, if we take it literally, then we produce the change and you have to adjust your coefficients, x1, x2, and others, to compensate this. In other words, string theory, in order to solve this problem with higher derivative, string theory has to be the theory of everything. There cannot be anything in the world escaping from string theory. So string theory is not a physics, because physics is always theory of something. And string theory has to be theory of everything, or of nothing, in this respect of quantum gravity. So, of course, it's a question of choice, what you like, okay? It's not forbidden at all. And string theory is very interesting point, I think, because it has a lot of developments. And all the papers which I cite here are done by string theorists, which are like very serious people, much more serious than me, for example. Now, what is another possibility, an alternative to Zweibach transformation? Arkady Tsetlin, who was the author of the string, initial string paper, I would say, did the following observation in 95. That instead of making this term zero, you can combine them into this construction. Exponential minus 1 divided by box. It's strange because it's non-local, but it is free of ghosts. This theory has no ghosts, okay? And he showed that this resolves the problem of Newtonian singularity. And he called it solving the problem of black hole singularity. Regardless, it's not exactly the same thing, let's say, okay? So it means a little bit of more of freedom to the string theory, because string theory has a lot of freedom, but this is one more, okay? So then actually people, even before, like Krasnikov and Kuzmin and some other people, Tom Bowles, more or less at the same time, and then recently there were big set of papers by Modesto and many other people, suggested the following: let us start with constructing quantum gravity with these exponential terms, or with other terms, especially Modesto has very good classification of these terms. And all of these theories are super normalizable, like our polynomial model, and they are free of ghosts at the tree level. Then I wrote a paper at some point counting ghosts in the ghost-free theories. And I showed that actually no, because if you take into account loop corrections, then you find that typically if you have divergences, this is the situation. Why it is free of ghosts? Because the equation for the denominator is p squared, which is graviton whole, multiplied by exponential of p squared with coefficient. So exponential is never equal to 0, right? Everybody agree with me? Do you know that exponential of x is equal to 0? No, there is no such x. You are wrong. There is such x. If x is equal to minus infinity, then exponential of minus infinity is 0, right? If you go to complex plane, then we have infinite point. So what it means? It means that if you add loop correction, then instead of exponential, when all the ghosts are in the infinity and are absolutely dangerous, you get a lot of ghosts. So I show this in these papers. You basically have infinite amount of the ghost-like states, all of them typically complex. Okay, they may, for example, fill some circumference on the complex coil, but you have a lot of ghosts. So these theories are free of ghosts at the tree level. Once again, in strict theory is fine because you don't need to quantize anything. But if you are doing it in quantum field theory, then you have to be careful. I will not elaborate, so it's possible to be careful, but I will not go to this. Then, how people studied ghosts in the past? So the first paper belonged to Tom Bollis in '77. That he did these 3 famous papers about fighting ghosts. And then Salam and Stradic had very, very good paper, all very clear, okay? And then Antoniadis, Bollis, and some other people. And then Johnson wrote a paper called Sedentary Ghost Poles in Quantum Gravity, if I'm not wrong. And he shows that all this is not, it's correct, but it's not conclusive in the following sense. Just to say that, because the idea of these papers was the following. You start always with 4 derivative gravity. You add quantum corrections, and then your massive poles splits into 2 complex poles. And these 2 complex poles may be unstable. They decay in the asymptotic state. So you can form your in state without ghosts, then you generate complex pair of ghosts in the interaction area, and then in the out state they disappear asymptotically. Your theory has asymptotic S matrix with very good, but Johnson has shown that the methods which Tom Bollis used in these 2 papers and were not sufficient because he said one loop does not give you a correct result. You need to exert propagator of gravitational field. And we don't have access to the non-perturbative results in gravity. So we cannot do it. Now there was also very interesting preprint of Hawking alone, which he did not publish, who is afraid of higher derivative ghosts. He said the following: ghosts are not isolated particles, they always come together with gravity. So you have to modify quantum field theory such that you can take it into account. I was very excited. I went to some very important people, typically string people, and because all very smart people are from string theory, or almost, okay? And asked them, what do you think about that? And the answer, typical answer was that it's not serious, because there is no such quantum field theory, we don't have it. And this is true, this is true. That's why probably Hawking did not publish it. He published with collaborators something much weaker statement. But you can do something. And to do something, you need to start with a theory which has not 4, but 6 derivatives. 6 derivatives is a game changer because then you make, at the classical level, you can have complex forms. Remember what Johnson said. You need full information about Dresser propagator to get some conclusions. It's impossible. Sure, but in 6 derivatives, you have supernormalizable theory, and your poles at the classical level may be already complex. So what you need more, or basically you need to show that the quantum corrections don't spoil the structure of poles. And this was done in this paper with Modesto, and we just found the conditions to have complex conjugate poles. Okay, there are 2 possibilities, if you can imagine, for quadratic equation. You have either 2 real solutions or 2 complex solutions, conjugate. Okay. It's easy. And then we found that using Lie-weak quantizations, it's very important. We found that the S matrix, this is called optical theory, S matrix is unitary. Oh, we have to be happy, S matrix is unitary, not very. Because what means Lie-weak quantization? Lie-weak quantization assumes that your theory is closed. Your system which you quantize is closed. There is in-state, out-state, and it is isolated from the rest of the world. But in gravity, it's very difficult to be isolated. In gravity, if you have a particle, it starts to emit its own gravitons, or absorb gravitons. So in gravity, this approach of S matrix, for me at least, is not very convincing. So you need something else to understand the situation. And what is this? We can simplify things. Why we don't think about classical stability? Remember this Ostrogradsky and Deltman story. So let's go back to Ostrogradsky and look about stability. And in fact, people started to see the behavior of gravitational waves, which is exactly the perturbation, very early. It's like Starobinsky paper of '83. And then we started to do it with Fabris, Pelinson in 2001, then Hawking, Kertek, and Real also wrote paper very similar. And then we made some next step in this paper. And finally, with Philippe Saris, who was my student, we found some very interesting continuation. What is it? In these papers, people start exploring quantum effects on gravitational waves without quantum, with four derivatives, and never ever found any explosion runaway solutions. So we asked with Philippe how we make runaway solutions, and the answer was found easily. So you have to do the following. You have to, you see, this is a typical plot of the behavior, it's numerical, for initial seed of perturbation, which is less than half of the Planck mass. You see there are no growing bonds. Everything is very peaceful. Okay? So you have your solution, then it increases to 6,000 times, and then it becomes smaller and smaller, and there is no runaway. But if you put half of the Planck, k is in the Planck units, the frequency. If you have initial frequency comparable to the Planck mass, then you have an explosion of amplitude. So we understood that this is the secret. So why we don't have harmful ghosts? Because ghosts are not created, real ghosts are not created from the vacuum, as I told you. So if you put huge frequencies, you can wake up ghosts from the vacuum, and then you are destroyed. You have runaway solution. If you don't do it, everything is under control. Is it true that if you create the ghost from the vacuum, things end up very badly? Not exactly. Yeah, this let's go here. So, so you can see the following. If we take a trans-Planckian or Planck, like 4 Planck scale, initial seeds of perturbation, this was done with Patrick Peter from Astrophysical Laboratory in Paris Institute. So what happens is the following. But the universe has expansion very, very fast. We put here numerically 10 minus 3 of Planck mass, which is like 10 orders of magnitude more than inflation, just to have fast effect and not wait too much. So this is what happens, you see. First, the ghost makes more than 1 million increase in the amplitude. So it looks like we are going to end. But then the universe expands and things reduce, and you have no explosion. Why is that? Because in this formula, this is the formula for our perturbations. You see that K comes in these space derivatives of the H of the perturbation. And space derivatives of the H always divides by A squared. A squared is a factor of the metric. So what really affects the ghost is this Q, which is K over A. So if A is growing fast, then at some point ghost becomes harmless. But for this you need expanding universe, and universe must expand sufficiently fast such that this growth of metric perturbation does not destroy the symmetry of your background. Okay, for example. Still we have a question. Why our frequency in the universe, which is not doesn't have very fast expansion, must be restricted to the underplank frequency? Why we cannot have any frequencies we like and live normal life? This is an interesting question, and it would be interesting to have mechanisms for that. So, and recently people started to discuss such a mechanism, and it's related to the complex poles. So there is a following fact that people in QCD there are two big branches. One is latest QCD, when people they do everything numerically, and another is analytic approach. And the main analytic approach, as I understood, is that suggested by Nabor Nakanishi in this paper in '75, almost 50 years ago. And he said the following, that you can have quarks, and these quarks develop complex poles. And this complex pulse indicates that there is a bond state. So you never see quark as a free particle. You only see protons, neutrons, or mesons, or something like that. And this is an analytic indication to have a confinement. So we can remember these papers, which I already mentioned, which discussed exactly this, the complex state in 4 derivative series. But we know that in 4 derivative series, complex states are not something easy to get. So why don't we go to 6 derivative series? And recently, this Bob Oldham and these people, Frasca and other Koshev, discussed this also in 4 derivative series, and then Leonardo Modesta and his collaborators, Jean-Luc Calgani, they started to do it for 6 derivatives, and Gustavo de Brito from São Paulo also wrote some paper. So people said, okay, we have complex poles, we may have actually confinement of ghosts, which is quite a beautiful idea, and take into account the rest of the story, I would say this is unique possibility to fight ghosts on the fundamental level. And here we have this paper, which, as I said, is still under consideration in the journal. When we found a practically working model of bond states for ghosts. Gaston Crane, who is our main expert in QCD, doesn't like when I say confinement every time he corrects me. But bond state is correct, okay? So let's take this 6 derivative theory. What we can do, we can transform it into the theory of equivalent scalars, massless scalar with the mass m, and scalar with the mass m star, which are complex conjugates. You can go to our paper and see all details, including 2 different methods to transform to scalars and equivalent scalars and so on. Now, all these methods are based on what Max Banyata said you cannot do. That's why take your equation for auxiliary fields, integrate, and then put it back to the action. But this is what people basically do. So sometimes we do things which we are not supposed to do. So this is the equivalent theory. Then we put, instead of the potential, which we don't know, we put the simplest possible potential we like. Actually, QCD people know that you can put here another potential, and bond state is not going to change. And after that, we use the simplest possible method, and the method is the following. We just say, okay, let us look for this bond state. Okay, as I said, you can have another bond state like P1 plus P2 square or something. There were papers discussing this in the past. So then you calculate the green function for this bond state, and this means you look for the mean value of this product. And when we take it, it looks like that in details. Then we calculate the propagator in a standard way, make this Dyson resummation, okay, with this, this integral is something simple to calculate, make Dyson resummation, and arrive at this, this is Dyson resummation, and we arrive at this equation for the propagator. Now, what means you have a bond state? It means the denominator is 0 at some value m, calligraphic m, and at the same time the residue must be positive, as this pole. Okay? Positive residue plus pole means you have normal particle. Negative residue would mean you have a ghost again, a real ghost. So there is this representation, which is not difficult to obtain, but very difficult to analyze, I would say, because there are branch cards and things like that. So after we do it, the final result is like this. Yeah, this is the plot from the first version of the paper, because today yesterday we resubmitted the second version, which other plot. But this is horrible. I mean, you see that this plot crosses the 0 line in one single point. It's very important. Imagine if it goes back, then this is the negative derivative. I will show in the next transparency that negative derivative means positive residue. So we found in this particular toy model that, in principle, you may have situation with a bond state of 2 ghosts. Okay? If you have it, then you have to evaluate the residue, and the residue is like this. So you see here we have minus divided by the derivative. The derivative is negative, so the residue is positive. And so we found, using both analytical and numerical approaches, that in this range of coupling constants, remember that this is a strongly coupled system, and our tricks to get our non-perturbative results are a little bit risky, okay? But anyway, in this model with these methods, we have bond state. It means that in principle, you may have probably bond states even for gravity. Of course, it's a long, long way to see this, but it's not impossible. And what it means. So imagine everything works. Imagine like 100 years from now, people will say, okay, we have bond states out of this massive ghost, we don't have harmful ghosts. Which consequences we may have? This answer, we don't need 100 years, we can answer right now. Because first of all, Dwyer and his collaborators, they wrote a set of papers, this is the first one, about the world when there is an automatic cutoff parameter, cutoff limit on the density of gravitons. They don't care about ghosts and things like that. They have just theoretical interest. So you can see that people discuss this, okay? But if we go to cosmology, for example, then there is the following situation. People discuss in the literature, starting from Jerome Martin and Robert Brandenberger, the following situation. If somebody makes cosmology, you know that cosmological perturbations, if you go backward in time, they have growing energy, growing frequency. So if you go sufficiently far backward, you will find that all the observations which we are seeing, in all perturbations we observe, in the past has trans-Planckian frequencies. And they said, okay, let us make some conclusions out of this. But this actually made some problems, because like when I wanted to find authors for this handbook, I asked this and other people, nobody wanted to write a report about this activity because they said there are too many problems. Okay, and then there is paper with this Barbado, Barcelo, Garay, and Janus also, the same thing in black hole case. So this typically, if people start to look deeper, there are big problems with this trans-Planckian physics. And we can say that there is no problem. Why? Because if we go backward in time, we approach Planck scale, then instead of growing frequencies to infinity, we hit the point when you form a pair of ghosts, complex ghosts, they form a bond state, and then there is no further increase of frequency. Okay, so there is a normal, natural, let's say, cutoff on the frequency of gravitational perturbations. So you may say that the first output is that these problems disappear. This trans-Planckian physics will not be ever observed. But there is another possibility. You see, you get particles, you get a classical gas of particles of mass Planck mass, and these particles have no charges, no electric charge, no any other charge, except mass, which is great because it's exactly the best candidate for to be dark matter, right? Not exactly, because if we evaluate the density of bond states, okay, using this simple formula, and compare it to the density of critical density of the state, like before inflation, then you find that there is 78 orders of magnitude of difference. So by the end of inflation, this gas was suppressed by this factor compared to the critical density, so it cannot be dark matter. And after I calculated, after this transparency was prepared, that after inflation passed some time, and 25 or less orders of magnitude were came back. So, but 50 is still a lot. So you cannot consider these bond states of gravitational ghosts as candidates to the dark matter. So it does not, it's not going to work.
There are 10 minutes left.
10 minutes. I thought I have to finish on time because it's conclusion.
Okay.
Okay, but then you can ask me whatever you want. So yeah, I came back to my normal rhythm because I saw time late. So Yeah. So what we can say as conclusions, first of all, that if we want to have quantum gravity, which is not restricted to the infrared region, to the low energy region, then we have to include higher derivatives. What it means exactly? Let me go back to the Simon approach. So this is this Simon approach to before. Yeah, this Simon approach says that all higher derivatives should be treated as perturbations. Actually, this makes sense because if we, as we see with Felipe Sales and with Patrick Peter, that if you don't put initial frequencies of the Planck order of magnitude, then the R-square term are always suppressed compared to R term, right? So it's not a crime to treat them as perturbations. It's correct. We had paper with Stravinsky when we explored, and my former student Flavia Sabrera and her student from Columbia, Anna, and we explored some theory using Simon approach. Actually, nobody did it before us. And at the same time, people from Recife did exactly the same theory. They were late like 1 month, but they did not consider it as small perturbation, as we did. We did it intentionally. And the results are the same, of course. So actually, it's not bad to treat these terms as small perturbations. You just need to understand that this means you put some cutoff to your energy of initial state of perturbation, no more than that. Then you need 4 derivatives if you go out of this approximation. So, second important conclusion that not only in quantum gravity, but even in semi-classical gravity, means if you do not quantize gravity, only quantize matter fields, you still have exactly the same set of problems with stability and unitarity. Unitarity no, but with stability as in quantum gravity. So nothing changes. So, yeah. Second, if we impose some restrictions on perturbations, like forbid the Planck density of gravitons, then we can live with ghosts. And finally, in principle, you can expect that in future people will explain this cutoff on frequency of ghosts by forming the bond state from these ghosts. And this, so we definitely have no solution to the problem of ghosts. Let me compare this to the situation with confinement in QCD. We don't have solution for the confinement analytically. But we have a lot of works which are very serious, and people believe that this is correct, okay? Because what is safe in quantum field theory is perturbative. And here we need something non-perturbative. So probably in this way we are going at some point to get something equivalent. So we are going to solve the problems of massive ghosts and physical ghosts, but this solution is not going to be very easy or very simple. Okay? So here I finish.
Thanks, Professor. We have time for 1 or 2 questions.
I'm sorry. So there appears massive ghosts, but would it be an issue to have like massive physical states, or?
No. If you have massive physical states, then imagine what will happen. The mass is one mass, right? So it will be like tensor particle which propagates interaction to the Planck length, 10 minus 33 centimeters. It's no problem, but no very big joy to have it, because we have no such distance.
What is the special property of string theory that specifically in that you were able to have a counterterm that eliminated all of the ghosts?
No. In string theory, it is completely different, I would say. Okay. So in string theory, you have the following situation. You have you have counterterms, okay, but these counterterms are all 2-dimensional because you quantize 2-dimensional object. So you have counterterm which change this term, and others. Yeah, and then you basically you have to calculate the trace anomaly, the called trace anomaly, and you require that this trace anomaly is zero, because if you violate while invariance, okay, it's not exactly trace while anomaly. Okay, if you violate while symmetry, then you have unphysical states in 2 dimensions. So then these conditions of cancellation of anomaly give you this effective action of sleep. Okay, in each order in alpha prime. Okay, and you can show that the correct way to do things, for example, is not to integrate, because your in string theory you have to consider both x and g, because they're functions of sigma, to be quantum. But you have to integrate first over x and only after over g. So it's very important, because if you integrate them simultaneously, you never get this action. No, you don't have, you start to mix these terms and these terms. So in the first order in alpha prime, you don't get Einstein gravity. You immediately get 4 derivative terms. Okay, and why? Because why you have to change this? Because like in QED, we integrate simultaneously photons and electrons. Okay, right? So why we have to in string theory include some order of integration? Because this corresponds to treating alpha prime as the expansion parameter. Okay, so you have to take this Polyakov approach that alpha prime is the loop expansion parameter. Okay, and then you have this order of integration, and you get your terms. But the counterterms I did not write here.
Okay.
But if I come back to 30 years of my life and start to calculate anomaly in this theory, then it will be different. But I'm not going to do it. Okay. But in principle, yeah, you calculate 2-dimensional divergences, renormalize and renormalize composite operators. This was very well elaborated by Zeitlin and other people before him and so on. And then you get your anomaly.
More question? Or?
I have a question. In this way of finding like the bound state of loss, is it also fine-tuned, like picking this Wilson coefficient in particular way such that you have those loss, like confined those?
Yeah, this is basically what the referee required us to explain.
Yes.
Okay, and I guess I know who is the referee. I know because I gave this in some conference and he asked me the same question. So I would say no, because the main questions are the following: what we can change in this scheme? Okay, and basically we can change a lot. But the main point is this: with this range of couplings, you don't need anything. You have still one single crossing the zero, okay? But if you change if you go take smaller g, then you are not going to have any zero. If you go beyond this, you might have a second zero and so on and so forth. So second zero would mean the positive, negative residue. So you basically have bond states with one normal particle and now one ghost, which is not a good deal because you gain nothing. So you need very fine-tuned situation. However, you have to be very careful because you see, if you take this, this theory with 6 derivatives, okay? So you note that this is a formula for the power quantum. So you see, even if P is 1, okay, at most you have 4 derivatives in the quantum. So you never renormalize the terms with the 6 derivatives. You renormalize only terms with 4 derivatives. Now, if you put n equal to 3, it means 10 derivative theory, which will have the same bond state, almost for sure. Then you only renormalize cosmological constant. It means that your theory is basically free from any correction, because cosmological constant defines the scale of the particles. Okay? So I would say that here there is no fine-tuning at all. Okay? What is you have to choose your coupling constants. And since all these parameters of the theory, imagine 10 derivatives, you have like 5 here, And if you want, you can introduce what Modesto and list of Rashford call killers and so on. So you have like plenty of parameters. And we need just one combination of these parameters which gives us the result. And then we say, okay, this is our theory. What may happen, maybe 500 years from now, then, is that people will have several perfect theories, or let's say 1 million perfect theories. But this, they will need experiments to separate them, okay? This is not, let's say, my problem of today, okay? So.
Well, let's thank the professor again.